Okay.
So hi students everyone. Good evening all of you. I'm cordially inviting you and appreciating everyone for who are all being here for this webinar session. And also hereby I'm glad to introduce our guest, Mr. Dr. Krishna M.E Singh, who has done masters and doctorate in IISc, and it's very a prestigious moment. And he is having a honorable profile of being a principal scientist in NAL National Aeronautics Laboratory Bangalore under the domain in structural integrity. So on behalf of Aeronautical Engineering students and colleagues, I am giving my warm welcome to you, sir, and please kindly proceed, sir. Thank you.
Thank you. Thank you. Good afternoon to
Students,
all.
yes, sir, proceed,
Hello,
sir.
sir. I want to go to seat just.
Hello, I'm audible, right?
Yes, sir, yes, sir. You can proceed, sir.
Yes. Yeah. Today's topic, I'm going to talk on this contemporary techniques in aircraft structural analysis and its present application related to our aircraft structures only. So we start with one Guru Shtotsam. Chaitanya Shashvato Shanto Vimvato Niranjana Bindunadi Kalatitaha Tasmai Shri Guruve Namaha. My salutation to the reverential teacher, who is verily the eternal consciousness, which is the nature of peace. He transcends space and time, the concept of zero, the primordial sound, and all parts. We know that zero was invented in India. Without zero, there is nothing like no calculation is possible. So with this Guru Shtotam, we'll proceed with our topic. Now coming to the basics, like what is finite element method, how the formulation take place. So we'll just show you the basic equation, that is Ku equal to F. In the case of how to derive the strain, the linear assumption of typical element, the axial strain, change in original length by the change in the length to the original length gives you the strain. So with that, this is the equation we get number one. So number two, what we are doing here is looking at the linear elasticity. We know stress is directly proportional to strain. We substitute the strain formula here. So that the change in length by original length multiplied by Young's modulus to get us the stress. So after getting the stress, we can compute the load, that is P, across the cross-sectional area of the any bar. Recognize stress is load per area. That is what we are used in the third equation. So coming to the actual problem, like you can see here, there are three bars which are connected at the top, and they are considered as the three elements having two nodes in each bar. So they are there's a force, resisting force, in all three of them, and then one is the force that is acting downward. So we have a equilibrium which is this is how we draw an equilibrium of the rigid body diagram of an equation where force has been equated in the equilibrium. So then we come to the next, the formulation part. We are going to continue with this free body diagrams. We have the resistance force minus F equal to 0, and then we had derived earlier the force which is 3 AU by L, which is the stress part. So the stress, it is change in length, the original length, the strain, and E is the Young's modulus. So we get stress equal to 0. So we can replace the stiffness matrix, which has a major role in any of the each of the elements. So K we represent as the stiffness of the spring or the bar, which is equal to 3A by L. When we replace that, we get the final equation, this equation number 8, this Ku equal to F or Ku minus F equal to 0. So with this background, I'm going to the what is meant by finite element analysis, what is multi-body dynamics, and how to do the static and dynamic analysis. So both are derived from the Newton's law of motion, where they use the force balance and the system response. Both use geometry as the starting point. Whereas in the multi-body dynamics, we look at the mass properties and define the connectivity. Whereas in the finite element analysis, we look at the geometry is meshed and represented as a continuum accurately. There's a continuity among all the nodes and elements. Overall system performance is seen in the case of multi-body dynamics, whereas in fundamental analysis we look at the structural response. It's called structural performance. So the characteristic is the motion of the system. We look at the multi-body dynamics, how the kinematics is taking place. That part we see in multi-body dynamics, whereas in the fundamental analysis we look at the deformation, stresses, strains, and the corresponding terms. Like in the simulation is a time domain and second one is frequency domain. So we get the Newton law, the mx double dot plus cx dot plus kx equal to f, where we get the acceleration is the mass and c is the damping, k is the stiffness, and x is the displacement. Is equal to the force. That is what we have derived only the part of it in the previous slides. Now we are seeing how the linear static when they substituted where force is zero, we get the linear equation f k equal to f. That is only called linear static. Non-linear when the k is a function of x. So when it becomes a function of displacement, the stiffness matrix, we get into non-linear part of it. And then free vibration where there is no damping, force vibration where all the terms are present. So with this background, I'll want to show some of the actual cases where the pressure has been aircraft pressurization taking place. In an aircraft, when you see when the engine air intake take place, where the high temperature pressure goes from the engine to the cabin. So the pressure is maintained by pumping air into the cabin. The air is bleed off of the gas turbine engine, then cooled and humidified before insertion into cabin. The pressurization cycles, along with the vibration, corrosion, thermal cycling, can cause petty cracks to form and propagate. So this is one of the important place like the cabin pressurization which take place, which can lead to the cracks to formation. Here you can see in the next slide, the air pressure inside the plane increases dramatically with altitude. This stress can weaken the plane's strength over time. So we can see in the first corner of the slide, when on the ground, air pressure is equal and outside the plane, whereas at the altitude of 35,000 feet altitude, inside the air pressure is greater than the outside, and the fuselage acts like a balloon. And the aircraft fuselage under repetitive cycles of differential pressure with each flight. The difference between the cabin and external pressure is around 6 to 7 psi we get at altitude of 36,000 feet. So we have to see that the cabin pressure altitude is maintained at 75% of the sea level pressure, which corresponds to an air pressure at 8,000 feet. So some variation of these numbers depending upon the aircraft model, it matters, and the construction details we'll see in the next slide about how the fuselage is maintained with this high pressurized cabin, and it is at a higher altitude. So here we see the pressure cabin is composed of the axial stress, the hoop stress, and the pressure inside the cabin. So this is a monocube construction where you can see the frame, the longitude, the longerons, the skin, the stringers, the bulkheads, and the fuselage terminates with the tail cone, but it's always maintained the lightweight construction. It's called the monocube construction. With this, you can see here the upper fuselage and the lower fuselage. They don't go into the similar pattern. Lower fuselage is subjected to corrosion resistance due to the air, when it lands in the rainy season, the lot of rainwater debris get imparted onto the lower part. The lower part is more prone to corrosion. The upper part is crack growth, residual strength, static strength, hoop stress, shear stress, all this combination of stresses that comes into the fuselage. So these are the dimensioning criteria for a long range aircraft fuselage. So here you can see one the classical example of an Aloha Airlines flight 243. It's a Boeing aircraft, which is 737. It has flight 243 between Aloha and Honolulu in Hawaii. It was Stephen suffered extensive damage after an explosive decompression in flight on April 28, 1988. The aircraft was able to land safely at Kahulu Airport in Mayu. There was one fatality, a flight attendant was swept overboard. So the fatigue crack that occurred due to the disbanding of cold bonded lap joints and hot bonded tear joints in the fuselage panels, causing the river to overstress. So a large number of small cracks in the fuselage are joined to form a larger crack. Corrosion also is a related factor. So here you can see how the upper part of the fuselage was torn away. Continuing on some of the examples like fatigue failure, the aircraft landing gear. The landing gear is shown here, this, designed to absorb the load arising from the taxiing, takeoff and landing. Landing is one of the most crucial parts where lots of loads come, then considered to the takeoff and taxiing. So hard landing shock is a particular concern, and fatigue crack can form in the strut and trinian arms as a result of shock and vibration loads. Again, corrosion can be a related factor in the case of landing gear. Here you can see the completely it is torn off into two pieces, the landing gear strut. Similarly, the failure of an overhead pulley retaining bolt on weightlifting machine, a manufacturer error has caused that forced the bolt to take the entire moment load and the bolt has failed. So here I am showing you the overview of how a fatigue or the fracture concept works. Like design work, it involves layout of the geometry of the structure, joints, material selection, material surface condition, the production variables. Then secondly come the basic information, the calculation of stress distribution, stress concentration, the SIF, the stress intensity factor, secondary bending, the stress life data, DADN versus delta K data, the fracture toughness, and the influence of surface conditioning, other production variables, supplemented. All these are basic information that goes into the analysis part. So the fatigue loads that come from the service utilization, the load spectra, the dynamic response, the stress spectrum, all these then environment variables, all these things are put together for a fatigue analysis. Then we come to the prediction of what is the fatigue limit, what is the crack initial life, what is the crack growth life, then the final failure. And after doing all this not only the complete analysis, which has to be supported by verification by test. So that is what finally, at least one or two tests we have to do. But the final analysis is done to minimize the number of tests. As we know that carrying out a test is an expensive thing. So here we see that the fatigue of structures, material, under small deformation, the yielding upwards within the limit load is called as a linear static. And then when it goes beyond the yield point, we get into the plasticity where permanent deformation happens. Other types of structural failure of buckling, where we can see the instability problem. Then fracture when it is broken into pieces, and the fatigue, which is a slow progressive failure phenomena. Then creep and the corrosion, which all lead to the failure of the component. So these are the different failure modes of a structure. So what is fatigue and fundamental analysis? It can be categorized into 5 box tricks. The failure under repeated or otherwise varying load, which never reaches a level sufficient to cause failure in a single application. So durability is a conglomeration of all the aspects that affect the life of a product and usually involves much more than just fatigue and fracture, but also the loading conditions, environmental concerns, material characterization and testing simulation, to name a few. So analysis process is a logarithmic. A 10% error in the load magnitude could result in a 100% error in the predicted fatigue life. So the input variables like material, loading and geometry, this has to be very accurate. The more your input is correct, the more will be the better will be your output. The post-processing of the results, they quite often leads back into 3 inputs to see what effect variations of these inputs will have on the life prediction. This is referred to as sensitivity analysis or what if study, whereby we changing the sensitivity, like some of the parameters we change and see how the behavior is changing. Useful at times when we're not quite sure about the accuracy of one of the inputs. So this sensitivity analysis we need to carry out in the case of analysis to have confidence in the results what we present. So coming to the basic design philosophies, we have a safe life, fail safe, and damage tolerant. These are the three basic. So here we have represented a spool where we have the service is a specific design life, where in the safe life we adopt a track is initiated and used on parts and components that are relatively easy and inexpensive to replace and not life-threatening if failure were able to occur. Most of the life is taken up in the initiation of a crack application ground vehicle industry. Even the landing gear, we do design based on safe life only. For landing gear, we don't go for fail-safe and damage tolerant because it is a large load carrying and there no cracks are allowed. So some of the critical components are designed even today with fuselage structure, where one of the frames may go off, still it will carry the load. So there, the fuselage structure is based on fail-safe and damage tolerant. So the philosophy is heavily on safety critical items such as aerospace and offshore industries. Coming to damage tolerant, where we have adopted in aerospace community mainly and nuclear power generation, it relies on the assumption that flaw is already existing and that a periodic inspection schedules have been ensured that the crack does not propagate to a critical state. So here only we get that fracture toughness, the stress intensity factor, the K1C, which we call derived from fracture aspect that comes under damage tolerant design philosophy. Now coming to the basic fatigue life methodology, as I said that 5-box trick, this is where we have a loads, material and geometry parameters put into fatigue analysis to compute the component life limit. So this is similar to the 5-box trick where we have the flight test and the coupon and component test also coming into the picture. So here we take on the basic constant amplitude load case. What is the stress range? Is difference of sigma max minus sigma min. What is mean stress? It is defined as the average of sigma max plus sigma min. What is the amplitude? Sigma A is amplitude, which is difference of max minus min divided by 2. Then K max, K min is nothing but K is nothing but the stress intensity factor. The difference between K max and K min gives you the delta K. From the delta K only we will get the DN versus delta K curves. Another parameter is stress ratio, which is sigma min by sigma max. So or K min by K max. So these are the various parameters one should know to know about the computation of fatigue part. So there are three types of basically the stress cycles. A static load R equal to 1 and R is greater than 0 and R equal to 0, 0 tension fatigue and R equal to minus is fully reversible loading, which is usually R equal to minus 1, which is less than 0. These are three categories of stress ratios which we will be studying it. So coming to the mean stress effect, the mean stress effect on the fatigue life. These are the different various curves on stress versus life, showing the typical stress amplitude life plots and the constant life diagrams for fatigue loading with non-zero mean stress effect. So we can see here the safe area and unsafe area, where we have the Soderberg, Goodman, and Gerber, and then Morrow. These are the four models where the fatigue limit strength sigma Fs relates to the Morrow, then the ultimate strength refers to the Goodman, and the yield stress refers to the Soderberg. So these are the three of them. And when we see that the amplitude of stress is within the curves, then it is within safe region. Once it falls outside, it goes into the unsafe region. So looking at the models like mean stress model, We have the Soderbergh, which is in 1930, where it depends on the yield stress, where the Goodman, which is again the sigma naught is the mean stress, and the sigma FL is the failure stress. It depends upon the ultimate stress. Where the Gerber also depends on the ultimate stress, but it is the parabolic curve, which is the square term. And the Morrow again is linear, but it depends on the failure stress. So the rule of thumb that we follow provides a conservative estimate of fatigue life. But most of engineering alloys, we go by Soderbergh relation. But Goodman gives very close observation for the experimental result for brittle metal, and it is very conservative for ductile alloys. And Gerber is generally good for ductile alloys. So these are just some of the thumb rules that have been listed here. So coming to the fatigue under variable amplitude loading. So constant is easy to handle, but variable amplitude is much more difficult. So in reality, aircraft components are subjected to variable amplitude loading rather than they simplify the so-called CAL, constant amplitude loading. The concept of damage accumulation, it determines the fatigue life of a component under these conditions, which requires a method to relate the variation in mean and alternating stress to the fatigue data obtained from constant amplitude loading test. The Palmgren minor rule, which is mathematical form, it is given by summation of 1 to m, that is the number of load cycles. NIF is the number of cycles for failure. Ni is the number of load amplitude that are applied in a given situation. If we do the summation and it is equals to 1, then we say that the failure has happened. It should be within 1. So the reciprocal of the fraction provides a measure of number of load spectra that a component can sustain before failure. This estimate is based on the assumption that the relationship between the small n and capital N is linear, and the fatigue life is dependent on the order in which the stress are applied. In most cases, these assumptions are marginally valid, and fatigue life estimates obtained from this Palmgren minor rule are adjusted through a testing or dividing by suitably a safety factors. Usually the scatter factor is the one which people use to take care of this uncertainty that is there in the model. The number of stress cycles imposed on a component is expressed as a percentage of total number of stress cycles of the same amplitude necessary to cause failure. Gives the fraction of the expended life. So in order which the stress block M, the different amplitudes are imposed, does not affect the fatigue life. Here again Ni, the number of cycles corresponding to the ith block of the constant stress amplitude delta sigma I in a sequence of M blocks. And NFI, the number of cycles to failure, is delta sigma I. The Palmgren rule, damage rule state that if it is equal to 1, then it is a failure. We have some other restrictions. All cycles must have the above fatigue limit. That means they are above the endurance limit. Valid only for, mostly for aluminum alloys, gives a life to crack initiation only. Valid only for R equal to -1. That is totally reverse cycle. So here we'll see one example. How do we compute this fatigue life for a given block of failure cycles? So in the first part, the variable amplitude loading is considered. We assume that sigma, the failure stress, the B is a constant 0.01 minus, and the stress history, one block of loading, and find the number of blocks to failure. We'll do the study with and without considering the mean stress effect. So first, without considering the mean stress, we have seen, suppose you take the first block of 80 as the delta sigma by 2, and number of cycles to failure as 24,735, and we apply the 100 blocks of cycles, we get an 0.004 as the damage fraction. So similarly, another block which is having delta sigma by 2 is 50, and number of cycles to failure is 27 lakhs, and 1000 cycles if we apply, we get a damage fraction of 0.004. Similarly, when we have another 50 blocks that is at the negative compressive side, the last one, we get the 27 lakhs, again we are applying a number of cycles to failure, and we apply only 1,000 of them, number of cycles that have been applied. So we get again 0.00004 as the damage fraction. So total we have to do summation. So we get as 0.0048. So with this we can say this type of analysis will say that around 210 blocks of this load this component can withstand. So we take an example here, a keyhole specimen, where we have modeled with all the three blocks, case 1, case 2, case 3. Case 1, we have taken the 80 as the load with 100 cycles. Case 2, 50 as the load, 1,000 cycles. Again, case 3 with 50 as the delta sigma by 2, 1,000 cycles, but it is in compressive mode. So all these three, when we model it, and we see that the results do match with the analytical here. So now considering the mean stress effect. So once you consider the mean stress effect, you see the number of cycles to failure. It is increasing. So we see that 24,000 as the number of cycles to failure, and 206, 437 as the cycles, and 21 each for 6 as the number of cycles to failure. We get as 112 blocks as the cycle. So concluding remark from this analysis is from 210 blocks to 112 blocks, it almost reduces by 53%. So we have to consider the mean stress effect. That is important for our analysis also. So that is being demonstrated using in this simplified example problem. So here I am showing one histogram plot for 100 flights consisting of variable amplitude load, how it looks like. Rainflow cycle counting has been done, and different blocks have been shown here. So here is another, the same problem continuing with the histogram where I have shown all the 7 cycles, 7 blocks of loading and their amplitude. And for a given D19 aluminum alloy, we know the stress amplitude, that is in MPa, and we know the constant amplitude cycle, number of cycles of failure. From that we can compute the small n by capital N, which will be the damage fraction. So percentage of damage also we can compute. So suppose we assume there are 100 flights, and then we get the total summation of n by n, small n by capital N, as 11.55 e raised to minus 3. We can compute the estimated life based on the 100 flights. So we come around 9,000 flights is the given for this component. So this is how we do a hand calculation of a fatigue. So I'm coming to the next is the problem of a case study of a landing gear. So where we can see the free edges of a landing gear, which has been imported from CAD model. So then we have done a FEA model. This is a tetrahedral mesh where we have the shown as a fixed boundary condition on the pintle pin as well as the actuator. These 2 points are fixed, and we have put a loading on the axle where we have a side load, the normal loads, and the drag loads. All 3 loads have been put here. One important observation is the toggle links, which are made up of aluminum, and rest of the material green in color is made up of steel. This is a picture shows that the nomenclature, FE model, boundary condition, material, and loads, all 3 of them are put here. So this is the what we have seen earlier, the 5-box clip. All 3 boxes are put in one model here. We like to acknowledge Mr. Manoj and Abdul, who are contributed to this work. It is not possible by alone doing this analysis, so we need take support from the students and the project staff. The same, the landing gear model can be modeled using 1D line models. See, the line model is superimposed the beam profile. It looks like as though it's a 3D model, but it's actually a line model which is being superimposed here. So here we are given the cross-sectional details, the beam cross-section, a cylinder, what is the radius and thickness, for the component, for piston, what is the radius and thickness, the stub axle and the actuator, pintle pin, yoke, and the axle. This is the axle here, and toggle links are modeled with the I section. So coming to the full cross-sectional view, when we see in the modeling how the boundary conditions are being given, and the loading is all similar to the 3D model. Here you can see the connectivity between the cross-sectional model where the bush is put between the lower piston and the upper piston. In between the liquid that runs around is the hydraulic part, which is compresses the when it is landing. It gives a shock absorber kind of shock absorber model. It is shown here. So the next is the mechanical properties and the aluminum and the steel. What are those properties have been listed here? You can see the ultimate strength 490 and 600, and the Young's model at 72 and 210. These are the various input parameters that one should be aware of before going for analysis. So coming to the some of the drag loads that has been applied. So these are the spin up and the lateral dip. These are the two cases we are studying now. The drag load, and whereas in the spin up we don't see the side load. Whereas in the lateral drift we see all three types of loads: drag, side and vertical. So when we do a convergence study, it is easy to do using 1D beam elements when we see that idealized. So when we have element size of 2.5, 5 and 10, we see that very good convergence we do get in the stresses and the output of stresses and the displacement. You can see 192.2, 192.7. So the stresses are showing within the 2% range, and it is showing very good convergence of the results. So coming to the similar pattern that what we show, this is the 1D model of the three models, where I'm showing you 185.7, 192.2, 192.7. So as the model decreases, the stress also is stabilizing. So the element size 10, 5 and 2.5 have been studied here. And this is the landing gear study where we have put the stress amplitudes on the screen. So showing the convergence mesh study of the mesh size, and the results have been shown here. So coming to the case study of the landing gear where we have a lateral drift and spin up, where you can see the spin up and the lateral drift is 220 here as the lateral drift, which is the more critical one compared to spin up, which is 175 as the maximum stress. So here I am wanted to show again this MPC, the multi-point constraint that we have provided here on the 1D beam element. If we provide at the bottom and the top, what happens in the scenario? So that is shown here to show that the bushing, the connectivity is similar in the cross-sectional view when you see, and in the actual models of the finite elemental model. So when we put this MPC, one MPC and two MPC, what happens? When we compare with the result with the solid model also. In solid model, we are not using MPC, whereas in the case of this 1D, one-dimensional model, we have used this multi-point constraint. Either you use one or two MPC, it makes not much difference. You can see the results are almost similar. 4.149 and 4.14 are the displacement, and the stresses are 60, 60, it remains same. So it is very much in the when it is sufficient to put maximum of 2 MPC because 1 MPC also gives similar results. So no need to go beyond 2 MPC. So MPC is nothing but multi-point constraints, as we seen in the previous slide input. Whereas for 5 different load cases, we have got the stresses and displacement. This is a comparison of 1D model with the solid model. So we do see some little difference in the stresses. 211, 220 as a solid model. So that this much of difference will definitely come when we model beam and a solid model. So coming to the little bit experimental part, here you can see we have put some 6 strain gauges to locate the strain values, and then we have a corresponding model of the nose landing gear. You can see that the strain values have been shown here, the strain distribution. So this is how we have put the 6 strain gauge location, 1 on the axle, 2 on the stub, 3 on the top, uh, fifth on the cylinder, sixth on the toggle link. So with those location here, 1 to 6, you can see here the axle, stub axle, the yoke bottom, top support, cylinder and toggle link. These are the 6 locations we are trying to capture the strain. When you capture the strain, this experimental result you can see in the third column, and the Fine-Tillman analysis results. Both are in microstrains for us to comparison easy. In percentage deviation, we can see the maximum is only around 3%. This is for a case of lateral drift, which is a critical load case, which we are studying. So we got very good match between the experiment and the Fine-Tillman analysis. So the coming to the multi-axial, like multi-axial is where we have all 3 types of load uh, simultaneously occurring, and their cumulative number of accidents also we have. This is a multi-axial state of fatigue analysis, where we have the nose landing gear is subjected to 3 direction of for different sink speeds. Sink speed nothing but this feet per second, that is given on the first column. So when this 3 of them, those multi-axial analysis, when we put the loads, it's a block load sequence, it looks like this. The spectrum what we see in the tabular column, when we plot it, it looks like this. And then the SN curves for 2 of the material, that is for the steel and aluminum, has been shown here. So coming to the what type of models we use for the multi-axial analysis are like maximum principal strain, it's called the Rankine, equivalent stress based model, these are, and the Tresca and the Von Mises distortion energy theory. These are the 3 types of models that we use for the multi-axial fatigue analysis. So we take a simple example of a full model or a half a model and a quarter model as a plate with a hole, which is generally the trend. So we can see that the stresses 364, 370 and 370. Either you model full, half or quarter, your stresses should come like this, which should be within a range of within some 2%. The 364, 370, again 370 in the quarter model. So this qualifies that your boundary conditions are correct and your loading and boundary conditions are correct and you are doing a right analysis, you are in a right direction. So less than 2% deviation, we are getting it. So coming to the damage model using this Goodman stress plot, the damage plots, where we can see that the maximum stress, Goodman and Von Mises, there is only critical plane which gives you very close relation with maximum principal stress. These are the life cycles for full, half and quarter model. So coming to the 4 load cases, what we have discussed earlier, we can see the data points and the stresses, no mean stress and the Goodman cycles. As we come to a 4th load cycle, it almost converges. So the load case 4 can be used with the least number of data points. So coming to the fracture mechanics by a single edge notch specimen, we can see this fringe pattern of a butterfly formation. This is nothing but elastic plastic analysis is happening. So these are the stresses sigma 11, sigma 22 and the Von Mises stresses. Von Mises stresses do give the butterfly pattern of the stresses. So with this model, when we come to actual model of a stiffened panel, like with stiffened and unstiffened panel, where we can see clearly that the half stiffened panel is FE model. When modeled, the curves which are shown here, see that we initially it's 500 then jump to 600 range. That is because of the stiffening of the panel. So it clearly shows 20% of increase in the strength of the compared to the stiffened and unstiffened panels. So here we are showing the crack growth, how the crack is growing using this extended Fine-Tillman method, where we can see the crack can grow through independent of the mesh elements. it can cross through the elements. So it can go through the stiffener, it can go through the basic plate alone, depending upon our modeling capability. So this extended funnel method gives an opportunity to model the crack as it grows. We can visualize the crack growth. That's the advantage of this extended funnel method, where we define the crack domain either as the skin or as the stiffened panel, the stringer. Or we can define the crack domain as both, then we can simulate the real scenario of crack growing either in the stiffener or in the skin panel. So with this, I'm almost coming to the last slide, where we actually pledge that we have to be as a bound to each other with love and respect. We serve in the army, courageous and disciplined, ever ready to fight against all low tendencies and false values we should not have. We should live honestly the noble life of sacrifice and service, producing more than what we consume and giving more than what we take. We seek the Lord grace to keep us on the path of virtue, courage and wisdom, and may the grace and blessing flow through us to the world around us. We believe our service of our country, the service of the Lord of Lords, and devotion to the people is devotion to the Supreme Self. We know our responsibilities, give us an ability, boldness, and courage to fulfill them. Thank you. Have any questions you can ask.